Hey everyone, welcome back to the channel. Today we're diving deep into the realm where the equations of physics meet the enigmas of philosophy. We're talking about those mind-bending experiments that not only unravel the secrets of the universe but also force us to confront profound questions about the nature of reality itself. From the iconic double-slit experiment, which first hinted at the bizarre wave-particle duality of light, to the enigma of Schrödinger's cat, where a feline exists in a blurry state of life and death, these thought-provoking experiments challenge our intuitive understanding of the world. They lead us down a rabbit hole of philosophical quandaries, questioning the role of the observer, the nature of causality, and even the very fabric of space-time. So buckle up, because we're about to embark on a thrilling exploration of the cosmos, where the lines between science and philosophy blur, and the universe reveals itself to be far stranger and more wondrous than we could have ever imagined. Let's begin. Our first stop on this journey into the quantum realm takes us to the double-slit experiment, a cornerstone of quantum mechanics. Imagine shining a beam of light onto a screen with two closely spaced slits. Now, common sense tells us that the light should pass through the slits and create two bright bands on the wall behind it, right? Well, that's not quite what happens. Instead, we see an interference pattern, a series of bright and dark bands, as if the light waves are interfering with each other. This is wave-like behavior, similar to how ripples on a pond interfere. But here's where it gets really strange. When we send individual particles of light, photons, through the slits one at a time, we still observe the interference pattern. It's as if each photon somehow travels through both slits simultaneously, interfering with itself. How can a single particle be in two places at once? This is where the quantum weirdness kicks in. The act of observation seems to play a crucial role. When we try to observe which slit the photon goes through, the interference pattern disappears, and the photon behaves like a well-behaved particle, going through one slit or the other. This observation-dependent behavior is one of the most profound mysteries in quantum mechanics. It suggests that the act of measurement somehow influences the state of the system. But how can our mere observation affect the fundamental nature of reality? The double-slit experiment has captivated physicists and philosophers for over 2 centuries. Does it imply that consciousness affects reality? Does it suggest that the universe is inherently probabilistic rather than deterministic? These are just a few of the mind-boggling questions raised by this seemingly simple experiment. It challenges our classical intuitions about the nature of particles, waves, and the very fabric of reality. And while it provides a glimpse into the bizarre world of quantum mechanics, it also leaves us with more questions than answers, fueling our curiosity to delve deeper into the mysteries of the universe. Prepare to enter the mind of Erwin Schrödinger, one of the pioneers of quantum mechanics, as we explore his famous thought experiment, Schrödinger's cat. Imagine a cat sealed inside a box with a diabolical contraption. The contraption contains a tiny amount of radioactive material with a 50% chance of decaying within an hour. If it decays, a mechanism releases a lethal poison, sending the cat to kitty heaven. Now, according to quantum mechanics, the radioactive atom exists in a superposition of states, both decayed and undecayed, until we make a measurement. This means that the cat, whose fate is entangled with the atom, is also in a superposition, both alive and dead, until we open the box to observe it. This thought experiment highlights the absurdity of applying quantum superposition to macroscopic objects like cats. After all, we don't observe cats walking around in a blurry state of life and death. But on a quantum level, particles exist in multiple states until measured, collapsing into a definite state upon observation. Schrödinger's cat isn't about animal cruelty. It's about illustrating the profound philosophical implications of quantum mechanics. Does the cat have a definite state even if we don't observe it? Does our observation somehow force the universe to choose between life and death for the cat? This thought experiment has sparked endless debates about the interpretation of quantum mechanics. Does it suggest that consciousness determines reality? Or does it point towards a multiverse, where every possible outcome of a quantum event branches off into a separate reality? While Schrödinger's cat may seem like a bizarre and morbid thought experiment, it forces us to confront the limits of our classical intuitions and embrace the counterintuitive nature of the quantum realm. It reminds us that the universe is far stranger than we might imagine, and our understanding of reality is constantly evolving as we delve deeper into the quantum realm. Fasten your seatbelts as we venture into the realm of quantum entanglement, a phenomenon so bizarre that even Einstein called it spooky action at a distance. The story begins with the EPR paradox, a thought experiment devised by Einstein, Podolsky and Rosen to challenge the completeness of quantum mechanics. Imagine two particles born together and linked in a way that their properties are correlated, even when separated by vast distances. Now, measure a property of one particle, like its spin. Instantly you know the corresponding property of the other particle, no matter how far apart they are. This instantaneous correlation seems to violate a fundamental principle of physics locality, which states that an object can only be influenced by its immediate surroundings. Einstein believed this spooky action at a distance implied that quantum mechanics was incomplete, and there must be some hidden variables we haven't accounted for. Enter John Bell and his ingenious inequality. Bell proposed a way to experimentally test whether local realism, the idea that objects have definite properties independent of observation and can only be influenced locally, holds true in the quantum world. Experiments based on Bell's inequality consistently show that the universe is inherently non-local. This means that quantum entanglement is real. Particles can be linked across vast distances in a way that defies our classical intuitions about space and time. But what does this non-locality imply about the nature of reality? Does it mean that our universe is interconnected in ways we can't even fathom? The EPR paradox and Bell's inequality demonstrate the profound implications of quantum entanglement, challenging our understanding of causality, locality, and the very fabric of space-time. These concepts force us to re-examine our assumptions about the nature of reality and embrace the mind-bending possibilities that the quantum world presents. Chapter 4. The Delayed Choice Experiment. Rewriting the past with quantum decisions. Get ready to question the very nature of time itself as we explore the mind-bending world of the delayed choice experiment. This experiment, conceived by John Wheeler, takes the strangeness of quantum mechanics to a whole new level by seemingly allowing us to influence the past. Imagine a photon traveling towards a beam splitter, a device that can split the photon's path into two. Now we can choose to measure the photon's path before it reaches the splitter, or delay our choice until after it has passed through. Here's the kicker. Even if we delay our choice until after the photon has seemingly decided which path to take, our measurement still influences the outcome. It's as if our choice retroactively determines the photon's behavior in the past. This defies our classical notion of causality, where cause precedes effect. How can our present observation affect a past event? Does it mean that time, as we perceive it, is an illusion? The delayed choice experiment, much like the double-slit experiment, highlights the peculiar nature of observation in quantum mechanics. It suggests that the act of measurement doesn't merely reveal a pre-existing reality, but actively participates in shaping that reality, even if it seemingly involves rewinding time. This experiment challenges our understanding of the temporal order of events and raises profound questions about the nature of time itself. It forces us to confront the possibility that the past is not fixed and that our present actions can have a retroactive influence on events that have already occurred, at least on a quantum level. The delayed choice experiment is a potent reminder that the universe is far stranger than we can imagine, and our journey into the quantum realm is just beginning. It urges us to question our fundamental assumptions about time, causality, and the nature of reality itself. Chapter 5. Mach's Principle and Relativity. The universe as a cosmic dance of matter and space-time. Prepare to have your perspective on the universe shifted as we delve into the fascinating interplay between matter, space, and inertia with Mach's Principle and its influence on Einstein's theory of relativity. Imagine for a moment that you're the only object in the universe. Now, try spinning. Can you tell if you're rotating if there's no reference point? This thought experiment lies at the heart of Mach's principle, proposed by physicist and philosopher Ernst Mach. Mach argued that inertia, the tendency of an object to resist changes in motion, isn't an inherent property of an object itself, but rather a consequence of its interaction with all the other matter in the universe. In a universe with only one object, inertia wouldn't exist. This radical idea deeply influenced Einstein's development of general relativity, which describes gravity as the curvature of space-time caused by the presence of mass and energy. Einstein incorporated some aspects of Mach's principle, suggesting that the distribution of matter in the universe determines the geometry of space-time itself. While Mach's principle hasn't been directly proven, it raises profound questions about the nature of space, time and gravity. Is space-time an absolute background in which the universe plays out, or is it a dynamic entity shaped by the cosmic dance of matter and energy? Mach's principle challenges our intuitive understanding of motion and inertia, suggesting that we're fundamentally interconnected with the vast cosmic web of matter. It highlights the interconnectedness of the universe, where the distribution of distant galaxies might subtly influence the motion of objects here on Earth. This principle serves as a potent reminder that our understanding of the universe is constantly evolving, and even seemingly fundamental concepts like inertia might be intricately linked to the grand cosmic structure of the universe. It encourages us to question our assumptions about the nature of space, time, and the fundamental forces that govern the cosmos. Chapter 6. The Quantum Suicide Experiment, a thought experiment in immortality, many worlds, and the persistence of self. Hold on tight as we venture into the truly bizarre with the Quantum Suicide Experiment, a thought experiment exploring the implications of the many worlds interpretation of quantum mechanics, an interpretation so radical it suggests an infinite number of you might be reading this right now. Imagine a brave or perhaps foolish volunteer participating in a deadly game of quantum roulette. Each round, they face a quantum gun that has a 50-50 chance of firing. According to the many worlds interpretation, each time the trigger is pulled, the universe splits into two, one where the gun fires and one where it doesn't. Now, the volunteer's consciousness also splits, experiencing both outcomes. In the branch where the gun fires, their experience ends. But in the branch where it doesn't, they continue to exist, effectively becoming immortal from their own perspective. This thought experiment raises profound questions about the nature of self, consciousness, and the very meaning of existence. If the many worlds interpretation is correct, does it imply that we're all potentially immortal, constantly branching off into parallel realities with every quantum event? Of course, the quantum suicide experiment is just that, a thought experiment. We can't ethically or practically conduct it, but it serves as a powerful illustration of the perplexing implications of the many worlds interpretation. It forces us to confront the possibility that our reality might be just one of an infinite number of parallel universes, each representing a different outcome of quantum events. It challenges our understanding of death, suggesting that even in the face of seemingly insurmountable odds, a version of us might continue to exist in some alternate quantum reality. While the quantum suicide experiment might seem like a morbid thought experiment, it opens up fascinating avenues for exploring the nature of consciousness, the meaning of existence, and the potential for a reality far grander and stranger than we ever imagined. Chapter 7. Gödel's Rotating Universe and Closed Time Loops. A journey into the past, paradoxes, and the malleability of time. Get ready to bend your understanding of time as we explore Gödel's rotating universe, a mind-boggling solution to Einstein's equations that allows for the possibility of time travel, at least mathematically. In the 1940s, mathematician Kurt Gödel presented a solution to Einstein's equations of general relativity that described a universe that was rotating. Now, this rotation wasn't like anything we observe in our own universe. It was a cosmic-scale spin that affected the very fabric of space-time. Gödel's solution suggested that this rotation would warp space-time so much that it would allow for closed time-like curves, essentially pathways through space-time that loop back on themselves, allowing objects to travel back into their own past. While Gödel's rotating universe doesn't accurately describe our own universe, which doesn't seem to be rotating on a large scale, it opened up a Pandora's box of possibilities and paradoxes. If time travel were possible, what would happen if you went back in time and prevented your own birth? This classic paradox, known as the grandfather paradox, highlights the potential logical inconsistencies that arise when we tamper with the unidirectional flow of time. It forces us to confront the limits of our understanding of causality and the nature of time itself. While Gödel's rotating universe might seem like a mathematical curiosity, it serves as a potent reminder that the universe is far stranger than we might imagine, and our understanding of time is far from complete. It challenges us to question the rigidity of time as we experience it and consider the possibility that time travel, while seemingly paradoxical, might be physically possible within the framework of general relativity. This exploration of Gödel's universe reminds us that our journey into the mysteries of the cosmos is far from over. It encourages us to keep an open mind, embrace the unknown, and continue to push the boundaries of our understanding of the cosmos. Chapter 8. Wigner's Friend, the Quantum Observer Effect, Subjective Reality, and the Limits of Objectivity. Prepare to question the nature of objective reality as we delve into the mind-bending world of Wigner's Friend, a thought experiment that takes the observer effect in quantum mechanics to a whole new level of philosophical complexity. Imagine a physicist, let's call him Eugene, conducting a quantum experiment in his lab. He has a friend, let's call her Alice, inside a sealed room, observing a quantum system, perhaps a single photon hitting a detector. Now, before Eugene opens the room to ask Alice about her observation, he describes the entire system, including Alice and the photon, as being in a superposition of states. From Eugene's perspective, Alice hasn't yet made a definite observation. However, from Alice's perspective, she has already observed the photon's state. This difference in perspectives creates a paradox. Are there two realities, one for Eugene and one for Alice? Or does the act of observation somehow collapse the superposition into a single, objective reality? Wigner's Friend experiment highlights the fundamental mystery of quantum measurement and the role of the observer. It forces us to confront the possibility that there might not be a single, objective reality independent of the observer. This experiment challenges our classical intuitions about the world, where we assume that there's a single, objective reality that exists independently of us. It suggests that quantum mechanics might require a more nuanced view of reality, one where the observer plays an active role in shaping the outcome of events, and where different observers might experience different realities. Wigner's Friend experiment serves as a potent reminder that our understanding of the universe is still evolving, and even seemingly fundamental concepts like objectivity and reality might need to be re-evaluated in light of the strange and counterintuitive world of quantum mechanics. Embracing the quantum enigma where physics and philosophy converge. As we conclude our journey through these mind-bending experiments, it's clear that the realm where physics meets philosophy is a captivating and endlessly fascinating one. These experiments, often defying our classical intuitions, push us to expand our understanding of the universe and question the very nature of reality itself. From the wave-particle duality of light to the mysteries of quantum entanglement, these concepts challenge our preconceived notions about the world. They force us to confront the possibility that reality might not be as straightforward as it seems, that time travel might be more than just science fiction, and that our consciousness might play a more significant role in shaping reality than we ever imagined. These experiments, while deeply rooted in physics, lead us to profound philosophical questions about the nature of existence, the role of consciousness, and the meaning of it all. They remind us that the quest to understand the universe is a never-ending journey, full of mystery, wonder, and the potential for groundbreaking discoveries that could forever change our understanding of ourselves and the cosmos. These experiments not only push the frontiers of physics, but also deepen our understanding of fundamental philosophical questions about reality, time, causality, consciousness, and existence. They illustrate the inseparability of science and philosophy in exploring the universe's fundamental nature.